Alright, so what I'm going to do is I'm going to review the fundamentals for delta H, thermodynamics, and some of the other stuff, and try not to breathe too heavy in the process. So here we go. Why do we care about thermodynamics? It's one of the big topics in chemistry. Spontaneous process. The whole point of thermodynamics is the end of it is we're supposed to basically figure out what is a spontaneous process. Spontaneous process means that you don't have to add any extra energy to it or any stimulus. Great example would be a ball rolling down the hill. That would be considered spontaneous. A ball rolling up the hill obviously would not. So how do we do it? Well, if you look right here, the first thing that we do is we focus on our delta H, which is enthalpy, which is heat. So if you're looking at this chart right here, basically, or not this chart, but this diagram, if heat is leaving a system, we say it has a delta H value that is negative. We say it's exothermic. If heat is going into a system, we say it's endothermic and requires heat to be added. The key thing to remember is the SLG rule. As you go from a solid to a liquid, or to a liquid to a gas, the way you do that is you have to add energy, or enthalpy, delta H. So we say the sign for those processes are have a sign positive delta H value for an increase in heat energy. If you're going from a gas to a liquid or a liquid to a solid, we say the delta H value is negative because heat is being released. So when you look at that, well, remember, exothermic energy is going to be released. The new bonds are going to be more stable. Endothermic energy has to go in, so energy is required. The new bonds would be less stable. If you look at exchange of heat with the system, we just were talking about this. Heat going in has a delta H value that is, or a sign that's positive. Heat going out would be associated with a negative delta H value. One of the things you're expected to do is interpret an energy diagram or a reaction coordinate, which always has energy listed on the left-hand side. So we say if it's downhill, meaning the products are lower than the reactants, like you see right here, we say that is an exothermic reaction. If you look, anytime you have an energy coordinate graph where the products are lower, we say that it is an exothermic reaction because energy is being lost. If it starts here and drops down to here, that is a release or a loss of energy. You can actually measure from the reactants to the products level. That would be your delta H value, and it would have a sign that would be negative. An endothermic reaction we say is an uphill reaction because the reactants are here, products are here, so basically what's happening is you're adding energy. The difference between this level and this level again would be the delta H, but in this case, if you look over here, the value of energy is increasing, so energy is, or delta H is increasing, so heat is flowing into the system. That's how we measure or figure out from a graph delta H. One of the key things is delta H value, if you see it with a reaction, can be used as a conversion factor. If you look right here, they tell you that you're using 12.8 grams of H2. So I put my 12.8 grams of H2 in the grid. Then what happens is I convert it to moles just by dividing by the molar mass. I have moles of H2 right here. They ask me what is the enthalpy or the amount of heat released. Remember, when you look at a reaction, if you look over here at H2, the coefficient of H2 in this reaction is 1. So mathematically, the ratio of H2 to delta H is a 1 mole of H2 is equal to negative 184.6 kilojoules. Therefore, that makes a conversion factor. Where did I get the 2 from? Why is that a 2? I don't know why I wrote the 2 there. That's kind of weird. So basically, I would take this conversion factor, flip it over, insert it in here, and I'm able to calculate using stoichiometry, kind of a heat stoichiometry. I am able to calculate the amount of heat that is released from a reaction. One of the things you're expected to do, in fact, on your Kung Fu quiz, the back question, the free response question, the first part, that's what they're asking you to do. Next thing, if you look right here, we learned that there are 3 ways to find delta H. The first way is what's called heat of formation. That's products minus reactants. You're given a table, you look up the values. The second way to find delta H is through Hess's law. That is where we take reactions, flip them around, and cancel them. And finally, the last way we find delta H is through bonds broken, bonds formed. We'll get into that a little bit later. If you look right here, classic heat equation, except those people don't play for the, well, I guess Dwayne Wade still plays for the Heat. The heat equation, when you go to calculate any amount of heat, it's always going to be in joules. That's what Q represents. M is mass of an object. The difference between the final temperature and the initial temperature, that is your delta T. And finally, specific heat is a value that you plug in, and you can calculate the amount of heat. And it's given to you in your AP booklet. One of the ways is that we calculate delta H is delta H from heat of formation. How do we do that? You look up values on a table. The values on the table let you know compounds how much heat is either released or gained in their formation, typically released. So if you look right here, there's a table with a whole bunch of values. If you look, they're all compounds. Elements, if you remember, have a delta H value of 0. So be careful on a free response section. If they ask you to solve for delta H, remember the elemental value is going to be 0. Typically they do that a lot on the exam. Here's what a typical problem looks like. If you take this equation right here, they're asking you to find the delta H value. Well, what am I doing? Well, if you look right here, whoa, what am I doing? Hold on a second. If you look right here, the first thing I'm going to do is I'm going to look up the values in the table. So if you look at delta H, H2 right here, the value for H2 is going to be 0 simply because it's elemental in form. If you look at CO as a gas, if I go back to the table, CO as a gas is right here. I'll highlight it in red. CO as a gas is negative 110. So what do? I come back over to my table and I pop in 110 underneath here. The coefficient of this is 4. Remember, we're doing products minus reactants. So when you do delta H, I take all the products and total them. So I'm going to take the 4 times the negative 110, place it in right there. 8 times the 0 goes right there, and I have all my products are done. Then I got to go back and look up the values for all my reactants. So just pick one, like look at CH4 as a gas. If I go over here, CH4 as a gas is negative 74.81. So what I do is I go back over here, 78.41, the coefficient is 3, so when I go to set it up, it's 3 times negative 74.81, 2 times the value for water, and the coefficient of CO2 is 1. So I put all the different reactants there. I'm going to multiply, add them all together. I subtract the products from the reactants, and I'm going to get my delta H value. That's one way we calculate delta H. All right. Let's see here, keep track of my time. I'm going to skip that. Next thing is delta S. Delta S is entropy. One of the things we're concerned about also in thermodynamics is entropy. And so we do delta S two ways. You can calculate delta S using products minus reactants, and I'll show you that. Or you can do delta S by inspection. That's where you look at the sign, you figure out the signs based on two things, the SLG rule or the number of moles. What is delta S? Delta S represents entropy, which is disorder or measurement of randomness in a system. If you go from a liquid or a solid to a gas, we say we increase the amount of disorder. We say the delta S value is positive. What do the signs mean? If you remember, first of all, a spontaneous process, we say has a delta S value that is positive. So for example, if delta S is positive, what does that mean? It means that entropy is increasing. If delta S is negative, we say entropy is decreasing, and we say it's non-spontaneous. So if delta S is positive, it's associated with spontaneous. Delta S is negative, we say it's non-spontaneous. So if you look right here, we use what's called the SLG rule to determine it first. Look at the states of matter represented in the chemical equation. If you go from a solid to a liquid, or a liquid to a gas, we say that the sign for delta S has to be positive. Disorder is increasing. If you go from a gas to a liquid to a solid, any of those phase changes, we say the value for delta S is negative. Now remember, if we say something's aqueous, if you take a solid, put it in a solution, it's basically going from a solid to a liquid, or aqueous. So that is an increase in entropy. The other thing that happens is if only gases are present. If you look at an equation and you can't see any differences in the state of matter, that's when you look at gases. You have all gases, and so then what we do is we use number of molecules. Typically what we use is the coefficient. For example, in this one, if you look right here, let me erase some of this. If you notice, the first thing I see when I look at this is that the reactants and the products are all gases. So I cannot use the SLG rule. So what I do is I look at total the number of moles. Number of moles on the left-hand side is 1. Coefficient right there technically is 1. 2 on the other side. If the number of moles increases from left to right, we say the delta S value is positive. If the number decreases, we say the delta S value is negative. So if we look right here, here's another example of doing delta S by inspection. So let me erase some of this. Forgot to do that. Magic, not so much. So let's take a look right here. So if we're going to do delta S by inspection, I have a liquid here and a gas here. Using the SLG rule, I know that the delta S value is going to be positive. It's an increase. Going from a liquid to a gas is always going to be a positive delta S value. I have a gas here and a gas here. I have to look at the number of moles, or the coefficients. 1 on this side, 2 on that side. My delta S value is increasing, or entropy is increasing. Then you look at the next one. Gas, 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 gas. Again, I have to go by number of moles. If you notice, I have 2 on the left, 2 on the right. Therefore, we basically say there's no change in delta S. There's no change because there's no change in the difference in moles from one side to the other. And finally, the last one, I have a solid here that's going to a solid. You can't really tell anything, but the solid also, you can ignore that part of it. Focus on the solid going to a gas, applying the SLG rule. You would say the value for delta S, or the sign for delta S, would be positive. If you look right here, same thing, this practice exercise. You're trying to figure out what the sign for delta S is. So when you try and figure out the sign for delta S, you do this. I look right here, a solid to a gas, using the SLG rule. That has to be a positive delta S value. Look right here. I have a solid here going to a solid. You can't really tell, but a gas going to a solid would mean that would be basically entropy is not increasing, it's decreasing. So disorder is getting more organized, so delta S would be negative. If you look at the next one, a gas, gas, and a solid. Same thing. Using the SLG rule, you're going this way. Looking that way, your delta S value is going to be negative. Last but not least, they're all gases. Then you have to look at total number of moles. I have 3 moles on that side, 2 on that side, so therefore my delta S value is also going to be negative. All right. The more complex the molecule, if you have 2 molecules that are at the exact same temperature, then how do you decide which one has more entropy? The more atoms that are in the molecule, basically the more disorganized it'll be, or the more spread out the energy will be. So out of these 2, this one has 5 atoms, this one has 8, and they're at the exact same temperature, or the same, so that means they're at the same, well, they're at the same state, they're both gases. Therefore, I would say C2H6 has a greater amount of entropy. How do you calculate delta S? Delta S is a pretty simple calculation. It should remind you of delta H calculation. It's summation of products minus reactants. Key thing here is everything has a delta S value, even elements. So if you look at a problem like this, they give you this reaction, they ask you to calculate delta S. If you notice, you see oxygen right there has a value. Remember, delta S is always in joules. Be careful with the units. When you're doing the calculation, it's always going to be in joules. Products minus reactants. So I take the 2 products. I take the coefficients times the value that was in the table originally, multiply those, and add them all together. I get 591. Then I take the reactants, coefficients, times the value from the table, and then I subtract the 2. So products minus reactants, so 591 minus 596, and I calculate my delta S value. Comes out to be negative 5.2 joules per Kelvin. Since that comes out to be negative, I would say that my reaction is non-spontaneous based on the sign, not the actual calculated value. I'm going to stop right there, and I will load another episode for delta G.